it's my pleasure to introduce today's CITA seminar speaker, Professor Maura McLaughlin. Maura is a professor at West Virginia University and is an expert on neutron stars, their environments, gravitational waves that you can observe by monitoring pulsars, which she'll tell us about today. And yeah, she's a leader in nanograv and the International Pulsar Timing Array. So it's really a pleasure to have her here to tell us about some of the exciting results and the promise for the future. And I'll turn things over to you.
Thank you, Maya. Hey, everybody. It's really nice to meet you all. Hopefully after the talk, if we haven't met in person, we can have a chance to chat more. Yes, I'm going to talk about nanograv and our most recent results. How many people are broadly familiar with the results? Sort of like some of the room, but not all of them. Okay. Yeah, so the basic, big picture summary of what I'm going to tell you about is how we use high precision timing with large radio telescopes of radio pulsars to look for very tiny correlated perturbations in the times of arrival of the radio pulses due to very low frequency or long period gravitational waves that we think are most likely emitted from supermassive black holes at the cores of merging galaxies. So this little cartoon gives you like kind of the big picture summary of the talk. And I'm going to tell you about, there we go. This is the punchline. So this is the result that we achieved and published back in June of this year, so a few months ago. And I'm going to describe what this means. These are measured correlations in the times of arrival of pulsars versus the angular separation between pulsars, and this is the expected curve. So this is the big result that got us all excited back in June, the first evidence for stochastic background of gravitational waves at low frequencies. It was pretty fun. This is like pretty esoteric science, actually. So I was very happy to see lots of like major articles, like news articles, news agencies picked it up with this like sort of very poetic language, like space-time churns like a choppy seed. I think this one was my favorite, scientist articles in space-time, and you have to buy groceries. Anyway, so I'm going to tell you this story. Before I do, just a little bit about our collaboration. So I'm a member of NanoGrav, which stands for the North American Nanohertz Observatory for Gravitational Waves. So we have both US and Canadian colleagues. We were formed in 2008, about 200 students and scientists. We're a lot smaller than LIGO, but we're a lot bigger than we were when we formed in 2008. We're funded as a National Science Foundation Physics Frontier Center since 2015. We also receive funding from Canadian funding agencies like NSERC. We have a webpage, obviously, if you want to learn more about us. We're also part of a bigger international collaboration called the IPTA, or the International Pulsar Timing Array. This is basically a consortium of consortia. So it consists of nanograv and then our counterparts in Europe, Australia, and India. The collaboration in South Africa using the Near Time Telescope is just in the process of joining right now. Here's a picture of us from a meeting this past summer. So the big picture goal of what we're trying to do with low frequency gravitational wave detection is understand how galaxies have grown and evolved through cosmic time. So if you look at this standard picture of galaxy formation, galaxies are born, they're small, they're regularly shaped. With time, they grow larger and more regularly shaped. And we think this happens through galaxy mergers. So we think galaxy mergers are a really important part of the story of galactic evolution. And we can see lots of evidence for this electromagnetically. We can see galaxies that are gravitationally bound and in the process of merging. But there's a ton of like really interesting questions about the processes that happen on very, very small scales. So not when these black holes are separated by this distance, but by only like parsecs, right? So sub-parsec separations. We really don't understand the roles of gravitational waves, the roles of gas, stellar scattering, in bringing these two black holes together. This is something called the last parsec problem or the final parsec problem. Like, how do these black holes get close enough together to eventually merge due to gravitational wave emission? And obviously we can't, at a glance with electromagnetic telescopes, look at this galaxy and tell that it's the product of a merger. We have no way of knowing there are two supermassive black holes at the core, and that's where gravitational waves come in. So our goal is to detect gravitational waves from these extremely massive black holes at the cores of galactic mergers to try to understand the astrophysical processes that bring galaxies together. And there's a whole bunch of other cool exotic science that we can do with this too, but this is sort of like the overarching goal and the reason that we first kind of got into this business. Okay. So you've all heard of LIGO. You all know that there are many detections of compact objects with LIGO, right? So LIGO has detected something like 100 now compact object mergers. It's kind of hard to see, but you've all seen this plot anyway. So these are black hole masses here. And I'm just showing this because it's nice to talk about LIGO first before we talk about how a pulsar timing array works, because it's much the same idea, right? So LIGO has two arms that are perpendicular to each other. The arms are 4 kilometers long, and lasers, as you know, run up and down these arms. And the reason that these arms are perpendicular to each other is that as a gravitational wave passes through LIGO, gravitational waves perturb things in a quadrupolar way. So one arm will get a little bit longer and one arm will get a little bit shorter, because they're at a 90-degree angle to each other, right? And that causes the light travel times along these arms to be different, and that's picked up this interferometer here. And so LIGO detects these very small changes in light travel times due to gravitational waves stretching or squeezing the arms of this detector as they pass through. And pulsar timing arrays operate on exactly the same principle. Instead of using lasers, we use cosmic clocks. We use radio pulsars. So instead of a laser source, we have natural pulsations. Instead of measuring, like an interferometer, we measure the times of arrival of pulses from these pulsars, and we look for very small shifts in the times of arrival. They'll still show this same quadrupolar spatial correlation, just like LIGO. There's a few things that are a little bit different. One different thing in our pulsar timing array, well, there's some like super obvious things, right? Like our arm lengths are not 4 kilometers, they're thousands of light years. Our test masses aren't 40 kilograms, they're solar mass or 2 times the solar mass. One other more subtle different thing is that when a gravitational wave passes through LIGO, it stretches or squeezes the whole arm. In our pulsar timing array, we have many gravitational wave wavelengths in between the pulsar and the Earth. So when we calculate the perturbation, there's an Earth term to the perturbation, like what is happening to the Earth at the time the pulsar pulse hits the Earth. What's the gravitational wave perturbation then? And there's also a pulsar term. What was happening at the time that radio pulse left the pulsar? What was the gravitational wave perturbation at the pulsar? So we have these two terms of the perturbation that we need to worry about in pulsar timing, which is a little bit different than LIGO. Just like LIGO, we search for very specific angular correlations in arrival times. If two pulsars are in the same direction, then we expect correlated arrival times, right? So for these two pulsars, if the pulse from one of them arrives early, a radio pulse from the other one at the same time should also arrive early. At 90 degrees, we expect an anti-correlation, and at 180 degrees, we expect a correlation again. We expect correlated arrival times. So this is a little cartoon of the signature that we're looking for in our data when we search for gravitational waves. This is the exact signature. It's a little more complicated than that basic cartoon once you do the math of averaging over a distribution of pulsars and a distribution of gravitational wave sources. But you can see that at 0 degrees, pulsar angular separation, we expect a positive correlation. At around 90 degrees, we expect a negative correlation. And at 180 degrees, we expect a positive correlation again. So this is the signature that we are looking for in our pulsar timing data. It will only ever go to 0.5 because those pulsar terms are all just noise for this analysis. So this is specifically for looking for a background of gravitational waves. The pulsars are all at different distances. They're just a source of noise for this analysis. So this is pretty cool. Like when we see this signature in our data, and I'll show you that we are seeing this signature in our data now, we're detecting the effects of gravitational waves on the Earth itself, right? Not on the pulsars, which is pretty neat. So this was published back in 1983. This Hellings and Downs curve, as we call it, has been known about for a really long time. So this is something that astronomers have been working towards for many decades now. Just a little bit to put us in context with other gravitational wave experiments. We analyze data on very long timescales. So our most recent data set was 15 years. That means our peak sensitivity in gravitational wave frequency is 1/15 years. And so that places us in like 10 to the minus 8, 10 to the minus 9 frequency range. That's what we're called the nanohertz, the North American Nanohertz Gravitational Wave Observatory. You can see a sensitivity curve here for nanograv. So this is at 1 over our time span, and our sensitivity decreases on either side of this peak sensitivity. There's a spike here. Any guesses what frequency that is? Yeah, it's exactly 1 over a year, because we would fit yearly perturbations out in the astrometry fits for our pulsar timing models. We'll talk about this in a little bit. But the important point of this is what our strain sensitivity is just around 10 to the minus 15, so much higher than LIGO. So LIGO is all the way down here. LIGO is also, of course, at much higher gravitational wave frequency. You can kind of understand where this number comes from. If you take sort of an average timing accuracy for our pulsars, it's a couple hundred nanoseconds or so. We've been doing the experiment for 15 years, and this very roughly gives you our strain sensitivity. So it's about 10 to the minus 15. And the strain is sort of the delta L over L, right? The change in path length over the path length. You can see another thing here, which are 2 different populations of gravitational wave sources. So we're sensitive to black holes, just like LIGO, just like LISA will be. But we're sensitive to much, much more massive black holes. And we can detect them in 2 different ways. We can detect a stochastic background, so the sum of all of the gravitational wave signals from all the supermassive black hole binaries in the universe. We expect that to have a red spectrum. So even though this strain is higher, or higher frequency supermassive black hole binaries, like up here, there's many fewer of them. They move through the gravitational wave band very quickly. So we expect this stochastic background to have what we would call a red spectrum. So lots of power at low frequencies from the longer period, lower frequency supermassive black hole binary orbits. And we can also detect individual supermassive black hole binaries. So there's the stochastic background source, and there's also individual sources, obviously, which we're sensitive to as well. And this is obviously idealized. We don't expect there to be an equal number of individual binaries, overall frequencies. I'll show you some more, kind of more realistic simulations of this in a little bit, but we don't really know, because we don't know what universe we live in and exactly where these individual supermassive black hole binaries that we can detect are in frequency space. Okay. By the way, I'm perfectly happy answering questions as we go. If anyone has questions on these slides as we get through, just let me know. Okay, so that was sort of like the big picture overview of the experiment. And now I'd like to talk first about our observing program, how we time radio pulsars, and then I'll talk about our gravitational wave analysis, and then our recent results. So we observe about 70 millisecond pulsars. So millisecond pulsars are the very fastest spinning pulsars. The pulsars we observe have spin periods between about 1.5 milliseconds to 16 milliseconds, so in that range. We observe them over a wide range of radio frequency. We need to do this to correct for interstellar medium effects. There's some frequency-dependent ISM effects, and so we need kind of a lever arm in radio frequency to correct for those. So we observe at frequencies from 400 megahertz with chime to 3 gigahertz with the VLA. Most of our observing right now is done with the Green Bank Telescope in West Virginia and the Chime Telescope here in Canada. The data set that I'm going to tell you about is roughly half Arecibo data and half GBT data. So for many, many years, Arecibo and GBT were the 2 real workhorses of our timing program. And sadly, we lost Arecibo. We completely lost it in December 2020. That's when it collapsed. But we were no longer able to observe after August 2020 when one of the cables broke. So the data set that our most recent exciting results are built off of, we stopped that data set on the day we lost access to Arecibo, because that was a very natural breaking off point to say, okay, we're done with this data set, we're going to process it now. So everything, yeah.
Well, how much replacement will fast be for Arecibo for your purposes?
Well, that's a really complicated question. So there were about 10 pulsars that we were observing with Arecibo that we just can't observe with the GBT. They're just too faint. So we just can't do justice with the Green Bank Telescope. We put a small proposal into FAST to observe 6 of those with the FAST telescope. The data look great, it's amazing, but we can't get enough time as nanograv to even remotely, make up for the time we lost with Arecibo. Because we were getting thousands of hours a year on Arecibo. We might be lucky to get 24 hours with FAST. So we had a very small pilot program with FAST, but we can't get enough time to really use it as a replacement. What we hope, though, is that, and I'll talk more about this later, that as part of this IPTA, this international collaboration, we can actually work with our Chinese colleagues, and they're observing these pulsars for sure, so to actually combine all our data into this large international data set, and so make up for the loss that way. We've compensated a little bit also with a very small program on the Very Large Array, but again, we can't get a lot of time on the VLA. It's not really built for pulsars. It does a lot of other science, and they're not going to let us have thousands of hours on the VLA for this project. So right now we're a little collecting area poor. The CHIME data will do a lot, but it doesn't have nearly the collecting area of Arecibo, so it just won't make up for that sensitivity loss. And so, this leads me to this worldwide PTA observing program. So as part of our membership in the IPTA, we're also collaborating with colleagues in Europe, in China, in Australia, India, South Africa, to work to make these combined international pulsar timing array data sets. And all of these collaborations have observing programs much like the one on the previous slide. So anywhere from daily to monthly observations of anywhere from tens to 50 or 60 pulsars, something like that, at multiple radio frequencies. This is really an exciting international effort, which is involving basically every large radio telescope in the world is doing this project. So let me talk a little bit about pulsar timing, what we mean by that, how we make pulsar timing models. So this is a very simple cartoon to illustrate what we mean by pulsar timing. So at every epoch of observation of one of our pulsars, we'll go to the GBT, for instance, we'll point at one of our pulsars, we'll observe for a half an hour or something. And over that half an hour, we will sum every pulse at the period of the pulsar, and we call this folding. So we'll take a time series of data, and we'll just add up every pulse on top of every pulse, every other pulse at the spin period of our pulsar. We can't detect single pulses from pulsars in general, they're much too faint. And so this results in a pulse profile that has a very high signal to noise. We'll accumulate it over a half an hour. We measure a time of arrival for that pulse profile at a particular epoch. We call this a TOA. So these are sort of like the currency of pulsar timing. We're always talking about TOAs or times of arrival. And then we have a timing model, which accounts for all the astrophysical stuff that we know is happening. I'll show you an example of one of those on the next slide. Then we observe that same pulsar, say a month later at the GBT. We do the same thing. We calculate a pulse profile, and then we calculate a pulsar timing residual, which is the difference between when this pulse arrived at epoch, say, J, minus when we predicted it should arrive based on this timing model, right? And it's these residuals that we're going to search for gravitational wave signals. So gravitational waves should produce non-zero residuals because we don't account for those gravitational wave signals in our pulsar timing model. So this is an example of one of these timing models. So you can see for this particular pulsar, we fit parameters like astrometric parameters, rate ascension, declination, proper motion, parallax. We fit for spin parameters, the spin frequency, the frequency derivative. No matter how many times I look at these timing models, I'm astounded that we can measure things to these precisions. So this pulsar at this particular epoch has a spin frequency of 218.8118404171579 hertz. And we really do know that down to that last digit. It still astounds me after all these years. Similarly for these rate ascension and declination parameters. I mean, we measure things with just ridiculous precision. These dispersion measure parameters relate to delays through the interstellar medium. This is a binary model. So this pulsar is in an orbit with a white dwarf star. The orbital period is 67.8 blah, 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 blah days. There are some general relativistic parameters for this particular pulsar that allow us to measure the companion mass. This is the orbital period decay due to gravitational wave emission. So we build up timing models with all the deterministic stuff that we know is affecting our pulsar timing residuals. And you can get these, they're all online, they're publicly available. You can go to data.nanograv.org. If you do that, you'll get timing models for each pulsar. You'll also get times of arrival, which look like this. You'll just get a text file. These MJDs here, these are the TOAs for this particular pulsar. These are the errors here in microseconds. These are the radio frequencies. And you can also get pulse profiles. So this is the pulse profile for one of our millisecond pulsars at a particular radio frequency. And there's a ton of other science, of course, that can be done with all of this stuff, and it's all public. So I encourage you, if you're interested in these things, to go grab it and do stuff with it. So Nanograph releases data every few years. Our first data release back in 2013 was for 5 years of data, and it had 17 pulsars. So these are like pulsars along this axis and time along this axis. So our 5-year data release had 17 pulsars, our 9-year data release had 37, our 11-year had 45, our 12-year had 47, and then our most recent release here had 68 pulsars. The different colors are different radio frequency telescope. So you can see that since we started this experiment, we've been adding more and more pulsars with time to the array. We've also increased our cadence. So you can see maybe that like the lines were very kind of sporadic up here, and then they've got kind of a lot more solid because we've been increasing our cadence more regularly. There's some empty spots in here due to telescope shutdowns and upgrades. So these are the data that we look at and that we analyze to search for gravitational waves. These are examples of residuals. And again, these residuals are the differences between the measured times of arrival for a particular pulsar and the modeled times of arrival. So the time of arrival that our best model would predict for that pulsar. So I picked 3 pulsars. The different colors are different backends, so different telescope backends. The A things, if you're curious, and the P things are Arecibo backends. The A is Arecibo, the P is Puerto Rican, and the G are Green Bank backends. So these 2 pulsars are observed with both telescopes. This one's just observed with Arecibo. Couple things to notice. One is the scale of this y-axis. So this is in microseconds. And you can see, so this spans, it's 1 microsecond here. Our root mean square residuals are well less than a microsecond for all of these pulsars. So that's pretty good for objects that have periods of milliseconds. You can also see they're mostly consistent with 0. So this shows that our timing models are pretty good. They're more or less predicting the arrival times for these pulsars correctly. Are they perfect though? They're definitely not perfect, right? Like these aren't featureless. You can see that there are some points or even clusters of points that are offset from 0. You might even imagine you can see maybe some like wander in these residuals, right? You could imagine the presence of low frequency noise in these just by eye. You can see these aren't perfect. There could be unmodeled effects such as gravitational waves in these residuals. But we cannot look at just like a single residual plot for one of these pulsars and detect gravitational waves, right? Because there could be all sorts of other sources of intrinsic noise. We need to cross-correlate the residuals from different pulsars and look for that Hellings-Downs correlation, that very special quadrupolar spatial correlation. And so that's the experiment that we are doing with these residuals. So what will a gravitational wave look like in this data? So this is an example of what a gravitational wave would look like before, up top, and after fitting for a stochastic background or a single gravitational wave source. The 3 different colors are 3 different pulsars in just different directions of the sky. So we expect this stochastic background, and again, this is the sum of all the gravitational wave sources in our frequency band. We expect this to have a very red spectrum, so have a very long period modulation on our pulsar timing residuals. So we think it would look something like this, this extremely long, low frequency effect on our pulsar timing residuals. However, after we fit for our timing model, right, we're going to absorb a lot of this variation into our pulsar timing model parameters. So after fitting, it'll look something like this in these 3 different pulsars. We expect this to look like sort of quasi-periodic red noise in the pulsar timing data. For a single source, so say we have a single supermassive black hole binary, as long as the period of that supermassive black hole binary isn't covariant with something in our timing model, like a binary period or like 1 over a year, we are going to basically preserve that signature before and after fitting. So you can see for a single source for these 3 different pulsars, the period will be the same in the residuals of all 3 pulsars, but depending on the orientation between that pulsar and the Earth and the gravitational wave source, we'll have a different amplitude and a different phase for the gravitational wave signature. Make sense? And just a reminder about all the other things that are happening in our pulsar timing data. So we have gravitational waves. We have these deterministic effects in the pulsar timing model, like binary motion, parallax proper motion. But there's other sources of noise in the data that we can't correct for perfectly. And we can't do a lot about some of these, like unlike LIGO, where we can just go and make a better laser. We can't do that. Our pulsars are natural clocks. We can't really futz with them. So there's some things that are unavoidable. Pulsars are not perfect rotators. They have some kind of intrinsic pulsar spin noise. They have something called pulse jitter. So, these single pulses kind of jump back and forth in phase, or amplitudes vary. That's another source of noise. There are some extrinsic sources of noise, like scattering in the interstellar medium, variations in dispersion measure. We need to correct our arrival times for the motion of the Earth around the sun and for the gravitational tugs of all the other planets in the solar system. So we need to barycenter our times of arrival, correct them to the solar system barycenter. For that, we need a planetary ephemeris. They may not be perfect. We need very accurate clocks at the observatories. There could be errors, right? You could have a clock error offset. So all of these sources of noise are also happening at the same time as this gravitational wave background, which looks like another source of noise with different properties.
About dispersion measure variations, how useful is your data set for lensing events? The analogs, the radio band, ESCs.
Yeah, so we've seen some things like that in our data. So I don't have a lot. I talk about DM. I don't think I have a DM plot. But yeah, so we have one of my grad students, his whole thesis is on studying these DM variations. So we measure DM in sort of week-long windows for the data, and we can see linear trends, we can see annual trends, we can probe the solar wind, and there are some pulsars which have shown some, I don't know if I'd call them ESEs, because that's a very specific definition, and I don't know that any of them actually correspond to that, but we do see excesses in electron density occasionally, some associated with the sun, right? So we understand them, but some others that must be due to ionized clumps of gas, like moving along our line of sight. Yeah, there's a lot we can learn. I think there's several PhD theses you could do on just these DM variations. Yeah, so the point of showing this is just to show that we can indeed distinguish the gravitational waves from other sources of noise because they have very different properties. So, we have a big Bayesian noise modeling analysis, which can tease out, say, scattering and DM variations from other variations because they depend on radio frequency and these other ones don't. We can tease out pulse jitter from these other variations because we expect this to be completely independent from epoch to epoch, whereas the others will kind of smoothly vary from epoch to epoch. The other source of noise that looks most similar to gravitational waves would be an error in a planetary ephemeris, right? So say we had the mass of Jupiter wrong. That would be achromatic. It would be correlated in time. It would also be correlated in space, just like gravitational waves, but not in a quadrupolar way. It would be a dipolar way. So pulsars separated by 180 degrees would have anti-correlated perturbations, not 90 degrees. So this is a very kind of cartoonish outline of how we do our noise analysis. This is a slightly more detailed plot. So for each pulsar, in our 15-year data set, we come up with a noise budget plot like this. So this is for a pulsar with about 15 and a half years of observation. And we evaluate the gravitational wave power. Well, the residual power, not all of it is gravitational waves, the residual power. So these orange bands here are the power at a bunch of different frequencies in our pulsar timing residuals. And you can see that there is excess power at low frequencies. You can see those here. And we can fit a power law to these data. This is a broken power law fit. And then we can break it down into different sources of noise. So we fit for individual red noise in addition to common red noise. So this green dotted line for this pulsar is the individual red noise fit. It's very low for this particular pulsar. And this is the common red noise fit that we think is due to gravitational wave. We also can fit a white noise component. The important thing about this is that we can look at the Bayes factors for excess noise. So if the Bayes factor is much greater than 1, this would say you're not accounting for all the noise with your model, you're not doing a good job modeling the noise. But for all of our pulsars at all of the frequencies, these Bayes factors are about 1 or smaller, which means that this model of white noise, individual red noise, this common red noise is encapsulating like what is happening with our pulsar spectra, and our pulsar residual spectra well. And you can look at our noise paper. We have plots like this for all of the pulsars in the data set. As I'm looking at this, I'm thinking I should have picked a more interesting one. Like I naively picked like the best one, which has like almost no intrinsic red noise and very little white noise. It probably would have been more interesting to pick one that has like more equal contributions. I'll do that next time. But you can look at this paper and see them yourself. Okay, so I'm going to step back. So our most recent data set is the 15-year data set. I'm going to step back to our last data set, which was the 12.5-year data set, just because it kind of tells an interesting story of like how we were motivated to do the analysis in the way we did for the 15-year data set. So in our 12.5-year data set, we did this noise analysis where we looked for individual pulsar red noise and common red noise. And when we did that, we found that there was a very strong source of common noise among all the pulsars. So when we looked at these plots, we saw that there was a very strong, red dotted line contribution. Some of the pulsars had individual noise, but we saw common red noise that all the pulsars had. And when we say common, we mean in all of the pulsar residuals, it has the same amplitude and the same spectral index, right? So noise with the same amplitude and spectral index in all of the pulsars. That was really exciting. This is a plot that shows the probability density of a particular amplitude. CP stands for common process. It doesn't say GW yet because we can't say for sure this was gravitational waves. It was some common process in the data. And you can see right away that these probability densities are very sharply peaked around a particular amplitude. These different lines are different ways of dealing with the solar system ephemeris. And the reason we were so paranoid about this is that in our 11-year data set, the one before this, we had a strong source of common noise, but it ended up being due to the ephemeris. So that's why we tried different ways of modeling the ephemeris, just to show that it wasn't that. So we're sure it's not the solar system ephemeris. This was really exciting. The Bayes factor for this common process over independent red noise was really high, like over 10,000. Super exciting. However, when we look at this correlated power versus angular separation, this is what we get. So these black points here are the data. This blue dotted line is the best fit Hellings and Downs curve, and you can see just by eye that there's no obvious spatial correlation there. There was no obvious spatial correlation if we actually do the statistics either. So we do not see Hellings and Downs correlations. We can't say that this is we couldn't say this was a gravitational wave background back with the 12.5-year data set. However, we were very excited because all of our international colleagues saw this exact same thing as well in their data. So these show spectral indices and amplitudes for this common process in all of the collaborations, sort of like penultimate data sets, their last data sets. This is for the EPTA collaboration, this is the PTA, this is the Parkes Pulsar Timing Array or Australian collaboration, and this is a combined international pulsar timing array data set, and you can see they all have consistent values for the spectral index and the amplitude of this common process. I'll talk a little bit more about supermassive black hole binaries later, but the spectral index is also very similar to what we expect for a population of supermassive black hole binaries. So we were really excited about this. This little table here just shows the evidence for this common process. In the IPTA paper, this combined data set, it was 10 to the 8. So 10 to the 8 favor a Bayes factor of 10 to the 8 of this common process over independent pulsar noise. So there's definitely something going on. However, no real evidence for the Hellings and Downs versus just a common process, and definitely no evidence for other kinds of spatial correlations like a monopole, like something that's not at all correlated with pulsar angular separation, or a dipole like we'd expect due to ephemeris. So all of this is good news. Doesn't show these spurious correlations, can't quite see the Hellings and Downs in there yet, but we know that there is a source of pulsar noise. So once we all saw this in our data, we undertook a huge coordinated international effort. This started about 3 years ago or so, and we sort of had like kind of 3 ways that we could move forward with this analysis. One way was just all the different collaborations that are doing this experiment just do their own thing independently and publish it. Another way was that no one publishes their own independent results, but we combine all of our data first into kind of like an uber international data set. We didn't like either of those ways. The first one, because, well, wouldn't it be as a believable result if we all did it completely independently? We didn't like the second one because it takes a really long time to make these combined data sets. So we decided on a third way, which was that each collaboration will do their own independent analysis, but we will all publish together. We'll synchronize the publications to all come out at the same time. We also set up a committee that would look at all the different results from the different PTAs, compare them, do consistency checks, kind of share techniques, and make sure that no one was sort of like wildly off base from each other, and we were all, doing consistent things. Doesn't mean the same things. We use, different codes, different telescopes, but just make sure that we're all on the same page. Okay, so this is the result of this coordinated international effort. On June 29th at midnight, we submitted 18 papers simultaneously, appeared on the archive. And this was the result of like so many telecons at unsociable hours, and lots of communication, cross-checking. So this is really, really exciting. And so if you look at all the papers that were published, there were 4 gravitational wave background papers from NanoGrav, the EPTA, and these are the Europeans, the EPTA, the Australians, and also a paper from the Chinese Pulsar timing array, all at the same time, and then a bunch of accompanying papers on different things, like the noise modeling, the timing data, what it means for supermassive black hole binaries, what it means for exotic physics, et cetera, et cetera. Okay, so I already showed you this. This is the result that we were really excited about. You might look at this and think, those error bars are really big, and the match to that line isn't that great. And you'd be right. This is the very first time that we've seen this evidence in our data. However, we were really excited when we saw this because this signature of positive correlations at low angular separations, negative correlations at about 90 degrees, and positive correlations again at 180 is really unmistakably the signature of a gravitational wave background. So very excited. This plot in itself is not what we use to do the analysis. So there are 2,000 pairs of pulsars. So this is, and we use all those pairs to actually do this gravitational wave analysis. This is binned just for ease of viewing, really, just so you can kind of like, see the shape of this, because you wouldn't really see anything. We plotted all 2,000 pairs on this plot. So let's talk a little bit more about the significance of the result, and then of course, what it means. So to estimate the significance, we can do a few different things. We approached it in a bunch of different ways, and I've shown 2 plots here that are both based on phase shifts. So we basically take the Fourier components of those residuals, those pulsar timing residuals, and just randomly shift them in phase, which removes the gravitational wave signal, do the analysis again, and see how often do we get a Hellings-and-Downs curve of signals and waves equal to or higher than that one that we got. If we do that in a Bayesian way, where we're looking at the Bayes factor of the Hellings-and-Downs to common red noise, we get a significance of something like 3 sigma. If we do it in a more frequentist way, it's kind of closer to 4 sigma. We have a whole bunch of other ways we've done this. We've also scrambled the positions of the pulsars on the sky a whole bunch of times and done it over and over. So it's about a 3.5 to 4 sigma result. And the Bayes factor for the common process over independent red noise is about 10 to the 12. So really overwhelming that there is a common process, and pretty good evidence for gravitational waves, but we're being very careful not to call this a detection yet, because we'd like to see the sigma to be a little bit higher for a detection. However, I'm not there yet. I'm going to just skip this. This is very interesting. It just sort of shows our chain of thought with intrinsic noise to the common process to the Hellings-and-Downs process, that the Hellings-and-Downs is strongly favored over just a common process with no spatial correlations. We don't see good evidence for either dipolar or monopolar correlations. This is us trying to add seeing if there's evidence for a sine wave also in the data, like we might expect due to a single source. And right now there's no real evidence for that. Okay, let me talk about the spectrum and then talk about the results of other PTAs. And I think when you see the other results of the PTAs, you'll see that even though our result itself, is not at the 5 sigma level, the other PTAs are all saying very similar things, which is very encouraging. So this is the spectrum of that gravitational wave background. And so you can see that it is a very red spectrum. So this blue line here is the posterior for our spectrum. We're constraining this to be a power law. This dotted line here is the spectrum that we would expect for a population of supermassive black hole binaries, under the very simplest assumption that they are evolving only due to gravitational wave emission, so no other astrophysics happening in the system. And you can see it is consistent, but a little bit shallower, which means there probably is some other astrophysics happening in addition to just gravitational wave emission. So this is really exciting. It's also consistent with lots of other exotic things though, like primordial gravitational waves from early universe inflation, cosmic strings, domain walls, etc. And I'm saying etc. because I am not a theoretical particle physicist, but there are more papers, more references to our new physics paper than any other paper in our whole series, because there's lots of people that are really excited about all the exotic physics implications of the result, or all the different ways you can interpret this as some exotic physics phenomenon. Okay, so this is consistent with signals seen in data from other PTAs. On the right here is the result from the Parkes pulsar timing array. On the left here is the result from the European pulsar timing array. You should look at the orange points here. They have two different versions of their data set, and they see it in only a subset of the data, but this one subset of the data clearly shows this expected correlation, sort of kind of similar-ish scale error bars, maybe a little bigger than our nanograph correlation. And the spectrum is also consistent between the different pulsar timing array collaborations. So these different colors show spectral constraints from the three different papers. The Europeans and the Indians collaborated to do a joint paper, so that's the EPTA plus the NPTA. Orange is nanograph, green is PPTA, and you can see the spectral index and amplitude are consistent roughly between the three collaborations, and here are the three different spectra. There's some overlap in pulsars between the three different groups, but we use completely independent telescopes and observing systems. So I'm going to wrap up soon, but I just want to say a little bit about the astrophysics. So what can we actually say about supermassive black hole binaries? So what we do to do this is we simulate populations of supermassive black hole binaries under some astrophysical assumptions. We simulate a whole bunch of populations varying those assumptions and then compare them to the stochastic background we measure, right? So we produce a stochastic background based on different populations, compare them to what we measure, and then we can place constraints on those populations. And so we start off with things like some stellar mass function, some pair fractions, so the fraction of galaxies that have a pair of supermassive black holes at their core, some merger timescale. We assume some relationship between the bulge mass of a galaxy and its black hole mass. This is an example of different measured relationships for black hole and galactic bulge masses. We carry out binary evolution under different assumptions, gravitational wave only, for interesting astrophysics. And then we have a bunch of different models that we use to actually model the data, just like we do in nanograph. And then we use this to try to constrain these populations by comparing with our measured data. So I don't have a ton of time to go into a lot of details, but this is the kind of stuff that we can say about supermassive black hole binaries based on our measurements. So these dashed lines here are the number of supermassive black hole binaries, and the solid lines are the fractional contribution of those binaries to our stochastic background. And so some properties like mass ratio, initial and final redshifts of these binaries are shown. So what this shows is that our signal is comprised of very massive binaries. So like the kind of tail end, the most massive end of the supermassive black hole binary population. These different colors are the contributions to different gravitational wave frequency bins. It's composed of roughly equal mass binaries at redshifts of like 1 to 2 or so. Here's another way of showing kind of similar things. So this shows mass ratio, distance, separation, and these gray bands over here are the posteriors that were fed into the analysis initially. These blue Gaussians here are the gray bands are the priors, the blue ones are the posteriors. This is where we end up after the analysis. And you can see that we require like slightly higher masses than we guessed initially, right? So the main outcome of this is the amplitude of our background is higher than most models would predict. It's not out of the range of most models. This here shows a bunch of papers that have made predictions on the amplitude of the stochastic background. These are the ranges of amplitudes predicted, and this is ours. So we're in line with some models. We rule out a whole bunch of models. So we're at sort of like the high end of the mass range. So this is interesting. It's still very preliminary, but high masses seem to be favored, or just like a large number of binaries seem to be favored. One important point to remember, though, is that there may be multiple contributions to this background, right? So all of these assume that entire stochastic background is due to supermassive black hole binaries. It might not be. There might be a contribution from primordial gravitational waves, cosmic strings, some other more exotic source. How do we tell the difference? Like right now, we just can't. We have no way to discriminate between those different scenarios. However, in about 5 years or so, we think we'll be able to tease out two separate backgrounds, and one is at about 50% the amplitude of the first. I don't have time to go into lots of details with this, but this shows at about our 20-year baseline, we can measure the presence of a second background with a fairly significant base factor of like 100 to 1,000. So 5 more years, we should be able to tell whether there are two backgrounds, assuming one is about half as bright as the first one. The other trick is the anisotropy. So we expect supermassive black hole binaries at some level to be anisotropic, right? They're not going to be perfectly isotropically distributed through the universe. These cosmological backgrounds will be, though. Things like primordial gravitational waves will be completely isotropic. And we also see that in about 20 years, we'll be able to measure an anisotropic contribution to the background at about a signal to noise of 3. So like,
would most mergers be occurring at cosmic noon when merger activity is at its peak? Or?
Yeah, and when we think that the main contribution to our signal will be redshifts of like 1 to 2. Just when you kind of factor in the mass distribution with redshift, merger timescales, and then the 1/d dependence on the strain, on distance. We think roughly like 1 to 2.
And anisotropy affected by the finite number of sources that are going to be activated.
Yes. Yeah.
So it's a sort of stochastic. You're expecting a stochastic anisotropy.
Exactly. Yeah.
Yes.
Yeah. So it shouldn't match exactly that Ellington balance prediction, because on some level it should be a little bit anisotropic, whereas these cosmological sources will be completely isotropic. Okay. And I'll just end really quickly by just mentioning that we also do searches for single sources. So in addition to this stochastic background measurement, we can, look in different directions of the galaxy, and in any particular direction, place a limit. The way we've arranged this plot here is to express those limits in terms of a distance limit. So this tells you, like in this direction of the galaxy, we can say there are no supermassive black hole binaries in our frequency range, with masses of about a billion solar masses out to about 160 megaparsecs. Our sensitivity varies wildly over the sky because our pulsar distribution, those are the red stars, are really anisotropic. We need more pulsars in some directions. And you can see some putative supermassive black hole binary sources marked here. And we've done one kind of cool thing with one particular supermassive black hole binary. This is a binary in 3C66b. And this is a millimeter observation of this binary, which shows this periodicity that's been interpreted as a supermassive black hole. And from the electromagnetic observations of this, one can constrain the priors for the single source gravitational wave stars. We're much more sensitive if we have like an electromagnetically identified binary. We can start with those priors. And this plot shows this is this orange band here is the predicted mass based on electromagnetic observations. And these two lines are our most recent estimates. This is the 11-year, these are the 12.5-year. We are marching very close to that predicted mass range for our single source search for this particular galaxy. So that's really, really exciting. And we think in our next data set, we're looking at the 15-year data set now, we should be very, very close to this predicted mass. Okay, so I'll just end by very quickly going through these slides. For the next, decade, of course, we've just made this first detection of this, kind of evidence for this gravitational wave background. And that's, of course, not the end of the story. We want to be able to fully characterize it. And to do that, we need more pulsars. So we like to grow the number of pulsars in the array. We think our signal to noise is linearly proportional to the number of pulsars. So that can be a huge boon. We are commissioning a wideband receiver on the Green Bay telescope. So this is very exciting. Right now we observe in this frequency band here and in this frequency band here, and soon we're going to get this entire frequency range, which is going to make our observing much more efficient and make us much more sensitive to these interstellar medium effects. And this is happening very soon. CHIME data. So that last data set, the 15-year data set did not incorporate any CHIME data. And this daily cadence of CHIME is going to be really complementary to the monthly GBT cadence. And it'll improve our dispersion measure and scattering modeling. So this is the DM. So I have one DM plot for you. These are DM measurements with CHIME and GBT. The orange is CHIME, the blue and green are GBT, and the error bars on the DM are much, much better with CHIME because at a much lower frequency. So this is really exciting. And so we're working on incorporating this into our next data set. And of course, we need a replacement for RCO. We've really been pushing hard on this DSA 2000 telescopes. This would be 2,000 small dishes, probably in Nevada, in a valley in Nevada, with about Arecibo collecting area. We hope to get about a quarter of the time on this. And once we have a telescope like this, we will fully compensate for the loss at Arecibo. And this is really necessary, something like this, for us to get into single source gravitational wave science. This again shows frequency versus strain. The green is if we just do what we're doing. This gray band is the projected population of single supermassive black hole binary sources. This blue band is what we'll be sensitive to with the DSA 2000. So it's going to really change the landscape of this single source science that we can do. And I'll just end with a reminder that we also want to grow the International Pulsar Timing Array. We're working on a new data set that will come out before our next nanograv data set. And this combined data set will have our 15-year results, all the other PTA results, plus data from Meerkat and CHIME. And it should be an amazing data set and result in a very significant detection of this supermassive black hole binary background, and maybe a single source. And I will just end with this pretty picture, just reminding you all that the ultimate goal is, of course, multi-messenger astrophysics, right? Where we have many single sources that we're tracking both with gravitational waves with nanograv and through electromagnetic observations with other telescopes. And we expect to get to this multi-messenger astrophysics single source detection mode in a few years to sort of the next decade. So the future is bright. Just revamped our website and had an artist make all these nice pictures for us. So squeeze them into the talk somehow. I think they're so pretty. Yeah.
So would you be able to localize some of these myths for the multi-messenger whole?
Yeah, so that's a really great question. At first, not very well at all. So let me just step back and say that I think the first detections we make will be follow-ups, will be detections of things that are already localized, so sources that have been identified electromagnetically, and then we find them in our data. Then we probably will start detecting things blindly. We will not have very good localization at all, like many square degrees. And the reason for that is that right now we can only use the Earth terms in the analysis. Once we can use the pulsar terms too, then we'll be able to localize very well. But to use the pulsar terms, we need very accurate distances to the pulsars. And we don't have that yet for enough pulsars. Like we have that for maybe one pulsar. We just know the distance to within a gravitational wave wavelength, basically. But once we know the distances to the pulsar as well, and this should happen again in a decade to decades, we'll know those distances well enough to use those as arms in the detector, much like, LIGO localization is way better when you have multiple interferometers. And then we should be able to localize much better.
Just to follow up on the question, could you say a bit more about what you expect in terms of time dependence of the factor?
Yeah, it should be like...
You have concrete models of mergers and so on,
and
they spend a certain amount of time getting the semi-major acts.
Yeah, we expect it to be stationary because our sources are very far from merging, but they're still sort of millions of years from actually merging.
So these are the most massive black holes.
Yeah, but our background is, so we may have a few, it's kind of hard to answer, but because we don't exactly, you could get, possibly there's like a few very nearby, massive objects with short timescales that might be contributing to the background and would cause it to have some non-stationarity, but most of it will be dominated by the long period, low frequency population with very long merging timescales. So we don't expect the background to change with time, really. Expect it to be stationary. Yeah.
So, while reading the papers, I didn't quite understand how the Ellings-Downs measurement goes into the calculation, say, of the fitting like the supermassive black hole models to the gamma. Does it go into that calculation, or is it just the CUR and the red noise process that's going into the calculation?
The Hellings, so you're asking, like, does the Hellings and Downs fit depend on the gamma?
Well, I'm asking whether in the calculation of going from the gamma to the supermassive black hole constraints, does the Hellings and Downs come in anywhere in the data?
Not in our analysis. So to calculate the gamma, all we're looking at is that common noise process. Spatial correlations don't determine that. They're basically separate things. Like we see the spatial correlations, which says, okay, now we know this is gravitational waves. Assuming that, then let's go back to this common spectrum, and then assuming that's gravitational waves, use that to infer the supermassive black hole binary population.
Yeah, so one other question that I had is, you said that the signal to noise ratio goes as n, but what about the significance of the HD, like the Hellings and Downs correlation? Does that also go as n, the number of pulsars?
Roughly, I mean, we expect the significance of the signal to noise to roughly increase the same way.
Okay.
But the way we calculate the significance, we do this with like sky scrambles of the pulsars and phase shifts. So we don't have we do have an empirical relationship, but generally we do that an analytical relationship. Generally we do it in an empirical way, but it should roughly go linearly as well.
Yeah, the reason why I asked that question is because, like, again, as we were discussing on lunch as well, like it will depend on what separations between.
Yeah,
if you have something at the edge, maybe it's.
Yeah, I mean that's why I'm kind of waffling because it depends on like where the pulsars that we find and add are. It'll be a much different result if we find new pulsars in holes where we don't have any pulsars versus if we find a pulsar right where we already have a pulsar. Like we get more benefit from sampling at that. Like if you notice the Hellings and Downs curve, there are very large error bars on like the right part of the curve at wide angular separation. So we do better by filling in that part of the curve, for instance.
So is that factored into like strategies for finding new pulsars?
We're just starting to do that.
Okay.
Yeah, we didn't used to, but we're just starting to plan surveys like in those holes. We started a GBT survey called the GBNCC survey for the Green Bank North Celestial Cap survey. So basically no pulsars at sort of the northern celestial cap. There was this big hole at very high declinations. And now we found a few MSPs in that region, and that's increased our sensitivity.
There's a question online from Reed. Go ahead, Reed.
Hi, thank you for the great talk. This is actually, you just started talking about it, so maybe it's fortuitous. I was wondering if you could go on a little bit more about like the specific plans to find more pulsars. Is it just getting more time on telescopes pointed in the right direction, or is there any other specific technique?
Yeah, I mean, there's kind of two ways to go about it. One of them is just building bigger telescopes. If we build a bigger telescope with wider bandwidth, some pulsars that we even know of now might become good enough to add to the pulsar tracking array. So for instance, with this wideband receiver coming on the GBT, we plan to revisit lots of MSPs, which right now aren't good enough. We can't time them well enough, but maybe with this wide bandwidth, they'll be good enough. So some of this can be accomplished like without new searches. But then, the other thing we need to do is just survey the sky, which means telescope time. So we have a search going on now with Green Bank. We've really been hurt by the loss of Arecibo. We had some sensitive MSP searches with Arecibo that obviously we can't do anymore. The CSA 2000 instrument, we hope will also do pulsar searches. And of course, there's searches happening all over the world. FAST is finding a ton of millisecond pulsars. Meerkat will find a ton.
Sorry.
Well, that's kind of all I was going to say. Yeah. So some of them will become good with better telescopes and instrumentation. Otherwise, it really is just getting time for pulsar surveys.
Well, are you learned anything about correlations in red timing noise, it correlating with the strength of the magnetic field, the spin rate, the age?
Yeah, that's a great question. I wish that there was a one-to-one map between timing noise and spin down properties, so we could like find a pulsar, measure its period and period derivative and say, yeah, throw that one out, it's going to be bad. But so far, there's definitely not a one-to-one correlation. There is a hint that pulsars with higher EDOTs, so higher energy loss rates, spin down energy loss rates, have higher spin noise, but it's by no means, I mean, it's kind of, it's a scatter point plot with maybe a slight trend. To be honest, I think, I don't know if anyone has actually done that analysis. I mean, it's a very simple thing to do, but I don't know that anyone's done it on the new 15-year data set. We have some more measurements of red noise, so we should look to see if maybe that correlation has become more apparent. It's possible. Yeah, it's a great question.
Yeah, let's have one last question and then continue discussion upstairs.
Okay, the question is, you said if you only have one pulsar with a good distance, so what kind of distances do you want? What's the precision in distance?
Yeah, that's a good question. Yeah, so we need it to within a gravitational wave wavelength, which is about a parsec or so. And our pulsars are distances of roughly, kiloparsecs. The closest one is like a couple hundred parsec. So we need like 1 in 1,000 accuracy on the distance. We measure the distances through parallaxes, some through timing and some through VLBI. And we're getting close for a couple more, but they really need just like very long time scale VLBI campaigns or pulsar timing campaigns to get to the right level of accuracy. Yeah, and we don't need to get it for all the pulsars. If we just had even like 3 pulsars with really good distances, then we could include this pulsar term for those 3, and that would help us localize a lot.
Okay, yeah,